Okay, so now we are all getting ready to know how to run the simplex method more easily. We know the concept. We know we need to do those variable switching. We need to switch to the next basic feasible solutions. But here, we want to do it in an easier way, which is to update the linear system every time after we do a switch. Or in that particular example, before we run the second move, we want to update our system so that in each row, from row 1 to row n, there is exactly one basic variable, so that in row 0, there is no basic variable. The reason to do that is so that later, when we want to find entering and leaving variables, that's easier. Okay? So keep this in mind. Row 1 to row n, one basic variable. Row 0, no basic variable. When you see what happens in the next few slides, you will understand why we want to do this. So in other words, for those basic columns, which are columns that are corresponding to basic variables, we want an identity matrix in row 1 to row n, because in each row we want to have exactly one basic variable, and we want a zero vector in row 0. Okay, so recall our linear system here. This is the original one. We start from this particular solution, and the basic columns are the third one and the fourth ones, which is here. Right? You see that here we indeed have an identity matrix, which is good. And here, this is a zero vector. So basically, that's why for the first iteration, everything looks so okay, because we are satisfying our requirements. And then we know x1 enters and x4 leaves. x1 enters and x4 leaves. So that means the basic variable x4 is replaced by x1, and then the new basis becomes x1 and x3. So following that requirement, we now want to update the system so that in the first and the second row, we have an identity matrix, which means x3 should be here and x1 should be here. And in the zeroth row, we have a zero vector. So we want 1, 1 here and a 0, 0, 0, 0. And at the same time, we want to make sure that this one and that one, the two linear systems are still the same. So that means we want to do some elementary row operations to make this one become the next one, but maintaining everything the same. So that's pretty much Gauss-Jordan elimination or elementary row operations. From this one, we are focusing on this particular number and that particular number. We want to make sure that for column 1 and column 3, we have the identity matrix and the zero vector. Typically, if you have an original basic variable, which is still basic after an iteration, then there's no problem there. Because previously it's basic, so at that moment, it satisfies the conditions for the basic columns. And this guy is originally non-basic. So all you need to do is to fix the problems here for that particular non-basic variables. So that's why this particular number is so important. Okay, so important. We know we want to focus on this column because x1 is the entering variable. And we also know that we are talking about this one instead of that one because x4 is the leaving variable. So we call this intersection of column 1 and row 2 as the pivot. This particular number, we call it the pivot. Okay, so now what should we do? We want to make this number becomes 1. So we're going to multiply row 2 by 1/2 to get this particular format or here. Okay, that's row operation. And then multiply the second row by -1 and then add it to the first row. That's going to remove this particular x1. And all other values will change at the same time, of course. And finally, we want to remove this particular negative 2. So we're going to multiply constraint 2 by 1 and then add it to the zeroth row. Here there is a typo. This one should be 2. Okay? Because in step 1, we have already multiplied the constraint 2 by 1/2. So the coefficient here is just 1 now. And then we multiply 2 by 2 so that when we add it to the zeroth row, this number can be cancelled. So collectively, after we complete the 3 steps, your system would become this one. Okay? And we know updating this system also gives us the objective value z2 and the x2. Why is that? 8 is here. Okay? 8 is here. And this particular solution 4 and 2 is here. Okay? 4 is here and 2 is here. Why is that? We know x2 and x4 are non-basic. So they are zeros. So that's why your z is 8, x1 is 4, and x3 is 2. So doing the adjustments or doing the operations is good because it reveals important information about your solution and about your objective value. And what's more valuable is that now improving to the next basic feasible solution would become so easy. All we need to know is to take a look at the non-basic variables. For this one, if we increase x2, z would increase, that's good. For this one, if we enter x4, z would decrease, that's bad. So the only candidate is actually x2. And then, if we enter x2, then what's going to happen? x1 and x3 will be modified. Because x4 is still 0, we don't need to worry about that. But when x2 increase, we know x3 will decrease. When x2 increase, x1 would decrease. And each constraint would give us an upper bound to increase x2. And that particular upper bound obviously is the ratio of the right-hand side to the coefficient of x2 in the entering column. So that means we need to compare 4/3 and 8. And 4/3 is smaller, so that's why we will increase x2 from 0 to 4/3 and then stop. Okay? And then we know when we enter x2, we will hit 0 for constraint 1 first. x3 will become 0. So that's why we know x3 is the one that's leaving the basis, and x2 is the one entering the basis. So the basic variables would change from x1, x3 to x1, x2. So if we want to have x1 and x2 as the basic column, then we need to fix this guy. This number should become 1, and all other numbers should become 0. So I have the steps here, please double check, and then you will see that after the updating, you get this system. Again, this system is still the same as the original one, but now in a nice format because everything is revealed. x1 is 10/3, x2 is 4/3, and the z value is 32/3. Exactly what we want. Okay? And also, at this moment, if we want to do one more iteration for improvement, we check x3 and x4 because they are candidates. But if we increase x3, z would go down. If we increase x4, z will also go down. So that means entering either variable is bad, and that means the current solution is optimal. We are done. This solution is optimal because no other non-basic variable should enter the basis because none of them is going to increase the objective value. Okay, so that's the idea. If we find a non-basic variable to enter, then we check which constraint will hit 0 first, and then we get the pivot, we get the intersection. We do some row operations to clean out that particular column, and then we get to the next system, and then we do it again. What's even better is that for that particular simple exercise or simple example, we may check whether we are doing things reasonably by visualizing the iterations. We know that our initial basic feasible solution is 0, 0, whatever. We only care about those basic values or basic variables or x1 and x2 here because x1 and x2 are our original variables. So we actually start from this point, 0, 0, and then do one iteration to move to 4, 0, and then to do one more iteration to move to 10 over 3 and 4 over 3. By doing some graphical interpretation, you may actually check we are indeed moving toward the optimal solution and eventually stop at an optimal solution. And also we are indeed moving along edges, right? And we are really moving along extreme points. Every time when we stop at a basic feasible solution, that corresponds to an extreme point of the feasible region. So we are really implementing our concept with those algebra. So as a summary, to run the simplex method, first find an initial basic feasible solution and its basis. And then among all those non-basic variables with positive coefficients in the zeros row, choose one to enter. Now here, please be careful about this statement. When you are looking for a positive coefficient, what does that mean? That means you are trying to decrease your objective value. Okay? If you have a positive coefficient, then that means when you increase your particular variable, your z value would decrease. So this is valid when you want to solve a minimization problem. If you want to solve a maximization problem, then here you should look for non-basic variables with negative coefficients. Okay, keep that in mind. If you can find one, that can be your entering variable. If there is none, we can terminate and report the current basic feasible solution as optimal. Once we decide the entering variable, we need to calculate the ratios of the basic and right-hand side columns. We use the right-hand side values to divide the entering columns values and decide which basic variable should be the living variable. Among all those ratios, we choose the one that is the smallest. And then that gives us a new basis because we know which one should enter and which one should leave. So we switch. And then we make the system fit the requirements for basic columns to create that identity matrix and the zero vector. We do row operations to do that. And because we have that particular intersection called the pivot, so this process is also called pivoting. Okay, this is also called pivoting. And then we repeat until we satisfy this condition. That's the simplex method. We have some other things to supplement our discussions here, but let's stop for a while. Thank you.